Hey, I'd like to encourage you before you move on to this to really do watch this video, the one that I have linked before this. It will be very helpful. So this is page 516. The problem is that a family buys a new puppy. They plan to fence in a rectangular portion of their backyard. Here's our picture right here. They buy 60 feet of fencing, and they plan to put the fenced area against the house. So we only need fencing here and here and here. So our perimeter of this rectangle isn't actually all the way around the rectangle. Well, the perimeter is, but the amount of fencing that we need is just 2 widths and 1 length. We want to find the dimensions, like they're using the 60 feet of fencing. How wide should this thing be and how long should it be to get the greatest area on the inside? So number 7, if, for example, we make the width of this thing be 10 feet, how long will this length, this side parallel to the house? So recall we've got 60 feet of fencing. 60 feet of fencing. So 60 feet minus this 10-foot side minus this 10-foot side. 60 minus 2 10-foot sides. We've got 40 feet left for this length side. Now if we want to find the area enclosed by the fence, it's a rectangle. Remember with rectangles the area is width times length. So if we're going to say that my width is x, for any given width, what would this be? Of course, these two are going to be the same because it's a rectangle. So what would the length be? Well, let's think back to how we did this example. 60 feet of fencing minus 2 of whatever the width was. In this case, it was 10. So 60 feet minus 2 x's. So then our area is going to be width times length. So width, which is the x, times length. Now you may not recognize, but here we have a quadratic equation. Number 10 wants us to multiply it out so it's in a more recognizable quadratic equation form. So what I'm going to do is distribute. So I'm going to take the x times the 60 and the x times the negative 2x. So if I could draw lines on Word, I would do that, and we get this. Now we want it in this format where we put it in descending order of powers. So I'm just going to flip-flop these two terms, negative 2x squared and 60x. I'm just flip-flopping them, and there we go. We've got our typical standard formula for a quadratic equation. Now we want to know, what are the dimensions that will provide the largest area inside? In your book, it says to use the vertex formula to find it, but I'd like us to use an alternative method. Now, we know, especially if you just watched that video that I referenced, we know what quadratic functions look like. They're parabolas, so we max out, okay. The left to right thing. It's funny. So we know that it roller coasters up to the top and then back down. Or a parabola could also be like this. But we're fairly confident this is going to be one of these because we're looking for a maximum area. Minimums and maximums happen at the vertex. So if we've got a parabola like this, it's going to have a maximum right there at the vertex. If we had one like this, it would have a minimum at the vertex, but no maximum because it would go up forever. And it's not possible that the area could just go forever. I mean, we only have 60 feet of fencing. But let's just plug in numbers and see if we can figure out what the maximum is. As we plug in these numbers, they're just going to keep getting bigger and bigger and bigger until all of a sudden we max out and they start getting smaller and smaller. Now we could use a calculator or a spreadsheet. Whoops, that's not what I wanted. I'm going to go to Blackboard. Now, where I'm at, this link was, I think I had it up earlier by one of your exponential assignments, but I also have it on external links. And so way down here at the bottom, online scientific calculator. You could just use your calculator. So I'm going to plug in numbers for x, see what we get. So negative 2, oops, 2. Now we're going to plug in, let's start with 5 feet. Negative 2 times 5, plugged in for x squared, plus 60, plug in 5 for that other spot where x is. So do you see how this is our same equation? Negative 2 times x squared plus 60x, and I'm plugging in 5 for x. I'm saying, what if 5 is that width, right? This side, not this side. Let's see what the area is. It's 250. So let's try 10. Now, one nice thing about this guy is I can copy and paste. That'll save us some time. Let's try plugging in 10. Whoa! That is a lot bigger. Let's try 15. Whoa, even bigger. Now notice, I plugged in 5 and I had 250. I plugged in 5 more and it jumped up to 400. I plug in 5 more, 15, and it only jumped up 50 more. So notice how, even though we're putting in, like we did 5 more here, 5 more here, it's not increasing at a constant rate. That's different from a linear equation. A linear equation, if you're adding 5 numbers apart, or if you're plugging in 5 numbers apart, then all of your outputs should be the same distance away from each other. So here's another confirmation. This is not linear. Okay, let's try plugging in 20. Ooh, we've started to go down again. I think we found our vertex is somewhere between 10 and 20, probably somewhere around 15. Notice how it's kind of symmetrical. We have these two 400s on both sides. What do you suppose we would get if we plugged in 25? Something smaller. 250. Okay, let's narrow in on 15. So let's do like 13, 14, 15, 16, like all the numbers real close to 15. 13, 14, we're still going up so far. 15, still going up. Whoop, started to go back down again. So still, 15 seems to be our max. Now, what if it's not really 15? What if it's like 14.8? Let's zoom in a little more with the numbers that we're plugging in. Let's try 14.5. 14.5. 15. And let's do 15.5. We're still maxing out on plugging in 15. And notice how these numbers on both sides are symmetrical. We're 0.5 away in the x values we're plugging in, and we're symmetrical in the y values that we're getting out. The fact that it's symmetrical that way also makes me think that 15 really is that center top point, that it isn't just, you know, the hills slightly to the left or the right of 15. We could do more, like we could zoom in more and do 14.5, 14.6, 14.7. You know, we could keep zooming in more and more and more. But I'm going to call it good and say it's 15. Because I know within half of a foot that 15 is the max. But, you know, plugging into a calculator is one way we could do it. Let's try doing it on Excel. So remember, x was our side width side, and then we have area. So since it's Excel and we can just pull down, we might as well just go like 1, 2, 3, 4, 5. And so our formula, let's recall that real quick. Negative 2x squared plus 60x. And x is the width. So it's whatever's in this column over here, that's going to be my x. So negative 2 times the width, which is my x, caret 2, that's how I square it, plus 60 times, and then I want that x width again, click. So negative 2 times x squared plus 60 times x. Let's pull down, make sure it's doing what we want. Yep, okay. Let's just populate this thing. Huh, interesting. We got it down to 0. All right, so getting bigger, getting bigger, getting bigger, getting bigger, getting bigger. Whoop! There we go. 15. See that? 450. And now we're getting smaller, getting smaller, getting smaller. So these are all the numbers you would get if you took your calculator and you plugged in 1, then plugged in 2, then plugged in 3. We can see the value of using Excel, how it's so much faster. Let's graph this. Not because you have to. You don't for your homework. You don't have to graph this, but just to help us get a better understanding of what's happening here. So I'm going to pick a scatter plot. Look at that. Just what we expect a quadratic function to look like. I'm going to click on one of the data points, and I'm going to right click and add a trend line. Now, what Excel is doing is mathematically figuring what line comes the closest to all of these points. Like it's going through the middle of the cloud of points the best. This is the best fit line. Now, since that line really looks nothing like our data, we can tell this is not linear. It's not a linear pattern. Let's try our trend line. It's not even letting me try exponential because it'd just be so bad, I guess. So a quadratic equation is another name for it is a polynomial of order 2. So polynomial order 2, that's synonym for parabola. And we see how that just fits it so well. And we knew it would because it is a quadratic equation that we use to make all this data. Now, one more thing I'd like to caution you about. We're trying to find the dimensions that will provide the largest area for this puppy. So we came up with this number 15. X equals 15 was where a vertex was. And remember, X was the width length. So dimensions that give us the maximum area are 15 feet by, now if we look back at our graph, we might be tempted to say 450 feet. But remember, they only had 60 feet of fencing to begin with. That can't be it. Oh yes, remember this was area. So the dimensions that give us, let's say, a maximum area of 450 square feet are 15 feet by what? Well, remember this? That length. If this is 15 and this is 15, then we take 60 minus 2 15s, and it's 30. So 15 feet by 30 feet. There's our answer. Keep up the good work. You are so close to the end. Can you smell that finish line? Keep it up. You got this.